funny stuff. Before we start, actually, was there any questions from last course? As I said, it was a general motivation for this course. Now, today, mostly going to be speaking about strings and codes. Maybe, if we have time, we will go into the basics of probability theory. But strings and codes for now. A set of symbol A, written calligraphically, and which contains elements like AI for a certain I. Hi, Anita. Is an alphabet. Okay, so that follows the spirit of the Latin alphabet or any other alphabet. We have a set of symbols, which are our letters if we want. It can be finite. That is, my label I would run into this following set of index. 1, 2, ... n. In which case I would have capital N, different symbols. Or it can be infinite, in which case I is an element of the natural numbers, which I take to be 1, 2, 3, and so on. Now, just like we can do it with the alphabet, we can concatenate the letters into words. And we use the same nomenclature here for alphabets. So symbols can be concatenated. Into strings. Maybe I will forget once in a while, but typically when I define a word, I will tend to underline it in green. But strings are also called words. And I will use them interchangeably. Is that a word?
Interchangeably.
Interchangeably. I was missing a syllable. Okay, thank you, Will. My grammar coach. My English coach. Great, so by concatenated, I just mean you really just write down the symbols one next to another. Okay, you can formalize this with like fancy mathematical operations, but you don't even write an operation, it's just like the word concatenated itself has concatenated different letters like C, O, N, and so on. That's what I mean by concatenated. The set of all finite strings over an alphabet over an alphabet A is denoted A star.
The strings are finite, but there could be infinitely many of them because the set is infinite. The alphabet, rather.
The alphabet can be finite or infinite.
Yeah.
And then you can concatenate the symbols into strings, but the strings in A star have to be finite. That doesn't mean there's a finite number of members in A star, but it means that each member of A star has a finite length.
Yeah, okay.
Of particular interest, of course, is the binary alphabet. And I will always write it in its long form, like 0, 1. That's the alphabet. You know, some authors may use a fancy symbol to say, oh yeah, that's my, like the number 2 and bold faces. You might see that in some books, but I will tend to always write it like that. So that's, you know, it qualifies as an alphabet. It's a set of symbols. It has 2 symbols. It's a finite alphabet. And I call it, the binary alphabet. And as our first example of considering all strings over an alphabet, we can watch what 0, 1 star looks like. 0, 1 star, so it's going to give you a concrete idea of what we mean by the set of all finite strings. It's a set of all finite strings, and importantly, we will consider this one as a string. Epsilon it's called the empty string. It's the string of length 0, if you will. And then we have the strings of length 1, 0 and 1. And then we have the strings of length 2, 0, 0, 0, 1. What's after that? 1, 0, 1, 1. And then the strings of length 3, and this is where I'm going to stop. There are infinitely many of them. Yeah, I mentioned this one here is the empty string. And really it's just convenient to have it as a symbol, but it denotes the absence of a string, right? Nothing. And another comment I want to make is that that very ordering here, you know, I start with strings of length 0, and then string of length 1, and strings of length 2, and within each fixed length, like for example for the strings of length 2, I define a sort of an alphabetic order. I sort of decide that 0 is the smallest, and that will define the rest of the order. And so I have here implicitly written it. There's an ordering. It's not implicit, it's actually explicit, but sometimes when you write a set, you don't care about the order of the elements in the set. If I claim that the way I wrote them down in that set matter, well, it defines an order, and it's called the lexicographical ordering. Lexicographical ordering. Yeah, it really is like the alphabetic order. Any questions so far? Am I going too fast? Too slow? No. I assume it's stuff you might have seen in different contexts, but at least it's sort of prerequisites where we can speak the same language.
I've seen it before, but it's fine for review.
Yeah, exactly. Because if I start with the definition of a code and then you go like, oh yeah, what's an alphabet star? I can't, and then your mind is a bit bugged right away. So, okay, let me continue. I'll go a bit faster then. The following pair, we can have, there's a bijection. There is an obvious bijection between, right here, between the natural numbers and 0, 1 star, instead of all finite binary strings. And it's like if I would count them. So 1 will map to epsilon, 2 maps to, sorry, actually it's going to be easier if I go like this: 1, 2, 3, 4, 5, 6, 7, 8, and then I go like this. The lexicographical ordering: 0, 1, 0, 1, no, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1. Okay, so I can map them like this. Oh yeah, typically I will be writing through the course, I will mostly be writing natural numbers as, I will denote them with the letters N, M, L, not so far in the alphabet. So usually like N is going to be a natural number. And X, Y, Z will typically be strings. Okay, it's not I'm not promising anything, but most of the time that's going to be the spirit of the notation. So we've got numbers here and their corresponding strings. It's a bijection. I'm sure you know what a bijection is. It's a one-to-one mapping between two sets. There is countably many elements in that set, so there's a mapping with the natural numbers, and here is one of them. Now, it is so convenient to use this mapping that at some point I'm gonna use the number associated to a string without even writing it. That let's define the function which maps the string to its number, or vice versa, the number to its string. So we're going to be confusing strings and numbers at some point because it happens very often. And if you want to define mathematically the function phi, which takes an n to its corresponding string, then it just gets heavy because you have phi and phi minus 1s all over your paper. So it's just convenient to say, yeah, I know that I can map strings into numbers and vice versa, and I'm going to omit to define the proper mapping and to have it. Now, writing them down like this is one way to get them, but a convenient way to do it also is to look into the binary representation of the number n. So the number n written here, if I write it in binary, it's 1, and 2 in binary is 1, 0. 3 in binary is 1, 1. 4 in binary is 1, 0, 0. 5 is 1, 0, 1, and then 1, 1, 0, 1, 1, 1 for 7. 8 is 1, 0, 0, 0. And so you realize that the binary representation of the number n is qua string 1x. Right? Because if I write 1x, I write 1 epsilon. Well, that's just 1 qua string, because epsilon is the empty string. If I write 1 and then 0, that's 1, 0. And then 1 and then 1, that's 1, 1. And I stop here. Like you realize that one convenient way to recover a from a number the corresponding string is to write the number in binary and drop the leading 1. Which, by the way, is meaningless because in binary a number is always going to start with a 1. That's not true for numbers in base 10. They might start with a 7.
So is this a reason why you start the natural numbers from 1? Well, you can define it that they include 0 or that they don't include 0.
You're right. Yeah. And it's funny you asked the question because the main book that I said I will follow is Lee and Vitani, and they start their natural numbers with 0. I'm a trained physicist, and it always has bothered me to consider 0 as a natural number. So I'd rather start counting as 1.
Okay.
And so for me, the natural numbers is but their corresponding mapping is of course more ugly.
Yeah, because you have 0 that doesn't start with a 1.
Exactly.
But if you map epsilon with 0, string, so you get a length of string and number. So
If you map epsilon with 0.
yeah, because you are mapping 1 with epsilon.
Yeah.
But you can also add 0 and map epsilon with 0 and you map 1 into 1 and it's more.
Yeah, but then I lose this
Okay.
cute little trick
Yeah.
of saying write n in binary and then you realize that it's 1x. As I say, this anyways is just a trick. We're rarely gonna have to compute the corresponding number of a string, but it's good to have it like as a very solid basis. Oh yes, we can change numbers with strings and vice versa.
Do you ever miss a 0?
If I miss,
0, do you need it ever?
how do you mean?
Like, you're not using 0 as a natural number. Do you ever, like, need it?
Oh, well, worst case, if I would need it, I would say I'm going to consider the set of natural numbers union 0, or I'm going to use the real numbers or the rational numbers. I'm going to use the number 0. It's just that I rather have the set of natural numbers as 1, 2, 3, 4, 5, 6. Actually, yeah, I spent time writing it down here to make sure we speak of the same set. Is it more common for you to have natural numbers being 0, 1, 2, 3?
But it doesn't matter.
It doesn't matter. Yeah, that's...
If you do induction, you have 0 and then you have a successor.
The induction works also with 0.
Yeah.
But it works also if you start with 1.
Okay.
There is only to change the name.
It doesn't matter if it's bijective anyway.
It has the same structure.
Yeah.
No, you have 0 and epsilon. There you don't have both.
Oh yeah, I do. These are my strings. Epsilon 0, 1, 0, 0, 0, 1.
Yeah, but with that one, so you have the bin, your one. It's a mapping from n.
Yeah. So to compute bin of n, forget this column.
Yeah.
Because I take my number n here and I write it in binary. 1.
Okay, so how do you get 0? String.
Well, I don't need to.
Yeah, okay.
I don't need. My numbers start at 1.
So yeah, okay, you need like a unit for the concatenation with the so epsilon is acting like that.
Yes.
So you need sorry.
Some people who like mathematics, like you maybe Anita, but concatenating with epsilon in your set forms a monoid. You know, it's like an operation and it's closed, then you have a neutral element, which is epsilon, but there's no inverse of
You need that
concatenation.
when you're playing the set theory anyway, not this.
Yeah, okay, let me just add quickly that this relationship shall be implied. So that strings and numbers will be changed.
And in this table, your string number 8 is supposed to be 0. In the table of the mapping, the string number 8 is 3 zeros.
Oh, thank you. Yes, thank you. Correct. So the strings and numbers will be confounded, I should say. A string y, oh yeah, definition. A string y is a prefix of a string x if x equals y z for some z in 0, 1 star for some string z. Yeah, implicitly I'm assuming binary strings here. So a prefix really has the correct name. It is a prefix of a string. You know, the string x starts with y and has something else after z. A set S yeah, sorry, a set S subset of A star. In the end, I'm sort of keeping a general alphabet. Never mind. If you have written this, you could have just said A star. If you want to keep it general. So a subset of A star is prefix free if for all x and y in S x is a prefix of y only if x equals y. Okay, because from the definition you might notice that since epsilon is an A star, the empty word, z can be epsilon, which means that x can equal y. X is a prefix of itself. Okay, and now to define a prefix-free set, what we want to say is for any pair of strings in the set, no one is the prefix of the other. Well, of course, unless I have picked up the same string twice. That's the only thing it means. I could have said if x is different than y, and x and y are in S, then x is not a prefix of y.
So epsilon doesn't count as a prefix.
In fact, if your set S, you can show it, if your set S contains epsilon and some other element, then S is not a prefix-free set, because epsilon is the prefix of any other string. So, yeah.
So
It's interesting to have epsilon in a prefix-free set only if you only have epsilon, which is not interesting. No, sorry. It's not interesting to have only epsilon in a set. It's a set that contains only a single possible code word, and it would be the empty code word. But epsilon alone qualifies it as a prefix-free set. Okay, let me move forward. Yeah, just some examples. Yeah, okay. when I write down the natural numbers as I like them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I'm tired. Is that a prefix-free set?
No, because 10 has a prefix 1.
Correct. This one is the prefix of this 10. So it's not prefix.
What is your alphabet?
Yes?
So when you said natural numbers, do you mean them as natural numbers with this bijection or strings?
Actually, here I was quite on purpose. I didn't write that this set, I understand it as being the natural numbers. Because the natural numbers themselves, they don't care if they're written in base 2 or base 10 or whatever. I wrote this set as a set of symbols. As a set of strings. My symbol alphabet contains 10 elements.
Okay.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 symbols. All right. Okay. What could I do then? I could say 1 star, 2 star, 3 star, 4 star, 5 star, and let me continue a bit further. 10 star, 11 star. Is that a prefix-free set of strings? So what I've added here is I've considered it in an 11th symbol, star, which I use as an end marker.
It's still not prefix-free. Because we have to have for all the pairs that so one is the one star. No, actually,
It depends on the.
It's not prefix.
It is prefix.
I mean, it is.
It is.
okay, so we cannot have one star and then other numbers.
You can't get rid of the star.
Yeah.
Because the star is the end
Okay,
marker.
okay.
Yeah, you would need to have one
It's
star.
not
one.
a symbol. It's just.
No, exactly. I don't use star as I would use the digits. I use the digits to construct the numbers, and star is always my end marker. Because star is an end marker. Using an end marker is in fact a way to have a prefix-free set. Because every time you see the end marker, you're sure that okay, I've got a member, and it's not the prefix of any other one. Another way to get there, which is a very similar spirit, but it's to write them down like this. What of it? Yeah. 1 0, 1 1 0, 1 1 1 0, 1 1 1 1 0, and so on. This is also prefix free. It's the same idea. However, I'm encoding, if you understand those as the numbers, the natural numbers, I'm encoding the natural numbers in unary with ones, and I use 0 as an end marker. And it's a way to make sure I have a prefix-free set of strings. Okay. We now move into codes.
So that's why you have zeros in natural numbers. So if the arithmetic is a 0, it makes every natural number have a prefix-free representation. Because you have 0 as the final number in it.
I don't understand the comment.
Earlier we were discussing
whether 0 should be in natural
Before
numbers.
natural numbers, and in piano arithmetic, if you have a 0 and a successor, then if you write them down, you get this unary representation. And apparently it's also prefix free if you write it down like that.
I could add 0 here and it will remain a prefix-free set.
Mm-hmm.
But I don't think it changes anything to the debate whether 0 should be included as a member of the natural numbers or not.
I just observed that having 0 in makes all set of strings that represent this piano encoding of natural numbers prefix-free like that.
Okay. Yeah. It's like 1 can be understood in the sense of piano arithmetics as the number of times you take the successor to the number 0. Yeah. Fair enough. Definition. A code is a mapping E that goes from A to B star, from a source alphabet to a set of code words. B star. In fact, there are 3 things defined here. The code is the mapping, and then the domain of this mapping is what I call the source alphabet, A, and it maps it into strings of a different alphabet, B. So since they're strings, we use words. As I said, words is also a synonymous of strings, and we tend to call the elements of B code words. E stands for encoding. You will encode a symbol from that alphabet by that string, for example. Speaking of which, we will be interested in binary encodings. So we shall be interested mostly with binary code words. i.e. B star, sorry, my B is, it needs to be a calligraphic B. B star is 0, 1 star for our purposes. A could be a generic set, apple, banana, orange. It's an alphabet of 3 different symbols. Well, apple, if I write it, anyways, I could invent 3 symbols and encode these 3 symbols into bit strings. A code is non-singular if it is injective. So as a friendly reminder, that just says that if AI is different from AJ, then the encoding of AI is different from the encoding of AJ. And this permits an unambiguous decoding function. Unambiguous decoding. I'll just call it D equals E minus 1. Right? In fact, for some authors, you don't even qualify as a code if you're not an injective map. Okay, so to be a code, you need to have, you send the code words and it needs to be unambiguous. If I receive 001, was that apple or was that orange? If there's an ambiguity, then it's called a non-singular code for our nomenclature. I think that's a good place to go for a little break. Okay, let me go on.
Because 2 times 3 is empty.
In many situations, we want to encode sequences of source symbols. Which result into a stream of concatenated code words. Think of a communication channel.
Or Morse code, like you said earlier. A
Yep.
sentence in Morse code would be one of these sequence of alphabet letters
Exactly.
that are encoded in code words.
So yeah, exactly. Morse code fulfills this criterion. A is the alphabet of English, and it sends them into bits. It's either short or long, right?
Yeah.
So 0 and 1 if you want. And then when I'm going to write hello in Morse code, it's going to be the concatenation of H, the symbol encoding H, the symbol encoding E. Sorry, the bit string encoding
Code word.
H. Yeah, thank you. The code word of H, the code word of E, of L, L, O. And all that is going to be concatenated in the output. So this motivates, you were disappointed to have A such a small set. Don't worry, it's going to be bigger. We define the extension of the code. The extension of the code E defines a mapping that we call E star, but very often we're gonna forget about the star. Oh, E star goes from, it extends the code E. So E was only defined for symbols, Now E star is defined for strings of symbols. A star into bits. We're going to be interested in bits. Through the requirement that E star, if I have a sequence of symbols, which I'm going to write just as a S1, S2, Sn. So each of my Si is a member of A. It's a source symbol. Well, E star is encoded as E of S1 concatenated with E of S2 and so on, E of Sn. So that defines the extension of the code. And the code E, I'm still in definitions. A code E is uniquely decodable if its extension is non-singular. What does that mean? The extension is defined like this. So if there was a sequence of symbol to encode, that was a sequence of symbol. S1, then S2, then Sn. And I'm going to encode them in my channel through concatenation. I'm going to encode S1, encode S2, but the receiver is going to receive this stream of bits. He has to be able to uniquely, if this is non-singular, so that he manages to, in the end, find out how to break this into pieces and decode via the function d, which is the inverse of e, he will be able to decode unambiguously S1, S2, and so on, Sn. Then the code is said to be uniquely decodable. It is a stronger requirement of just being non-singular. One more definition before we go, and then we make a small example. E, again, E is a code. E is a prefix code. No, there's no space. Prefix free, but prefix code. E is a prefix code if E of A is a prefix free set. So you take the image of the alphabet, and it's a prefix-free set. In English, what does that mean? It means that no code word is a prefix of a different code word. Example. consider an alphabet of 4 symbols, capital A, capital B, capital C, capital D. This is our source symbols. To be encoded in bit strings. Bit strings. Sorry, I need space. In bit strings. We're gonna define 4 different codes. So I've got A, B, C, D. One code is going to be called E1, the other one E2, E3, and E4. E1 is 1, 0, maps A to 1, 0, it maps B to 1, 0, it maps C to 1, 1, and it maps D to 0. What can we say about the code E1? It's very bad.
Non-singular by itself.
Yes, exactly.
Or, no,
In fact, it's singular.
Yeah.
If you allow me to say that being non-singular means being singular. Yeah. So as I said, some authors will say it's not even a code. Because it's horrible. If you receive 1, 0, you don't even know if the guy meant A or if he meant B. Now we're going to do a bit better. Let's see. Let's encode with the code number 2, 1, 0, 1, 1, 0. So A maps to 1, 0, B maps to 1, 1, 0, C maps to 1, and D maps to 0.
It's not distinguishable.
Yeah, because CA maps to the same thing as B.
Maybe if I get 1, 0, I cannot distinguish if it's C and D or A.
There you go.
Yeah, or that. Yeah.
So it qualifies as a code, as a non-singular code, but this is where the property of uniquely decodable comes in. It's not uniquely decodable. It is non-singular, which so far so good, but as Matteo said, it's not uniquely decodable. Why? Because I'm just going to get some more space by writing over here. If one receives 1, 1, 0 as an input stream of encoded symbols, how should we decipher that?
Either B or CA.
Is it B? Is it CA? Yeah, it can even be CCD.
Yeah.
So this is where unique decodability comes in.
Is it going to be enough that the let me say this right? If all the code words is a prefix-free set, is that going to imply that the extension is uniquely decodable or whatever?
Yeah.
Okay.
So it's a set.
No.
It's
No,
more
I'm-
like-
Okay, so I took you through 4 definitions. Now you see me coming with my pedagogy, right? Like we have found the first code was horrible, it was singular. The second one fulfilled the second definition. It was non-singular, but it was not uniquely decodable. Now I'm going to come up with one which is uniquely decodable, but not prefix. It's not a prefix code. What is it? It is this one: 0, 0, 1, 0, 1, 1, and 1, 1, 1.
Okay, definitely not a prefix code.
It's not a prefix code.
Yep.
Because
A is the prefix.
This one is a prefix of these two.
Yeah, yeah.
This one is a prefix of this one.
But
So it's not a prefix code.
Yep.
But it's uniquely decodable, and I'm gonna leave it just for now. Sometimes it's messy to see why it's uniquely decodable, but we later on, if you let me first define E4, we're gonna revisit E3 in the light of E4. So sorry, I'm trying to miss colors. I'm gonna just say it's uniquely decodable here. Excuse me for my lack of space, but all these sentences refer to E2, and now the green one refers to E3. It just says it's uniquely decodable.
even though the
It's not prefix.
even though the code isn't prefix free.
Exactly, it's not a prefix code. Correct. And the fourth code is going to be 0, 1, 0, 1, 1, 0, and 1, 1, 1. This one is a prefix code. So just to recall the nomenclature, prefix code means that the code words is a prefix-free set. The code words is such that no code word is the prefix of another. Yet we don't call it a prefix-free code, we call it just a prefix code. So yeah, just for fun, let's investigate a possible input stream. No, sorry, output stream. We want to decode a bunch of bits that we receive. We receive a big string of bits, and we want to make sense of what was the input sequence. What was the source of these bits? So suppose that we receive 0, 1, 1, 1, 0, 1, 0, 1, 1, 0. And the code was E3. You realize that you can decode it. Why? Okay, let's try it.
Okay, it's a bit tricky. You have to read ahead. Sorry.
You have to read ahead. There you go.
First one is either A or B.
When I see 0 and then some ones, I'm like, oh, it might be A, it might be B, it might even be C, but then
There's 3 ones. So
no one starts with just a 1 and then a 0. So,
Yeah.
so in fact,
It's A.
because there was the only way to make sense of the beginning is to realize that I had received C. No.
No,
Sorry,
it's-
sorry.
it's
I'm making.
AD is the first 2 letters.
I was going ahead of me. Yeah. AD is the first letters. Why? This is why I wanted to argue it. Because if I think that B so far so good, it might be tempting to say that it's B. But then I have 1, 1, 0 as the rest. And no code word is 1, 1, 0. Or anything that starts with 1, 1, 0. So I have to backtrack and go and say, no. It was indeed A, and then D, and then we had fun doing it.
It has to be B because there's only 1, 1.
Correct, it has to be B.
And then the next one has to be C because it's 2 1s continuously.
Dit is if you start from the back.
That could
If you
be.
try to start from the back.
Yeah, that could be.
You stole my trick.
Good
Wait a
idea.
minute. I haven't. I'm not here yet at my punchline.
C
Thank you. This is C,
and then A.
and
is
then
the
A
last
again.
So you need to know where the back is. Start at the back.
You can come up with like uniquely decodable codes that you really need to read the whole string, and the last digit will go like so the first one was an A. You know, like you have to understand it as a whole if you read it from left to right. You will quickly realize the beauty of prefix codes. Prefix codes you just read it from left to right, and you know right away how to decode them. So suppose we have the same input stream. I say input. What do you mean input? It's mostly like the output. Like it's the output of the code. I receive those bits as an output, and I want to decode that. Sorry. And suppose that let's use green for different clarity. If the code is E4, what can I say? Well, then it's quite clear. We understand the logic of E4. I've got a 0 is either an end marker or I have 3 ones. You can sort of see it this way. So if your job is to decode Morse, like some people's jobs used to be that, you know the code so well that you're sort of fast at manipulating it. Imagine that you are tattooed E4, or you really work, you spend your life with E4. You're going to be able to read this from left to right and right away say, oh yeah, this has to be A. 1, 1, 1, this has to be D. 0, 0 has to be A, exactly. 1, 0 has to be B. And 1, 1, 0 has to be C.
Sorry, but this will work with A3 from right to left only because the code works if you read them right to left are prefix free. Otherwise, it will not work in general.
If you read it on the other side, correct.
So they're suffix free?
That's
Yeah.
E3. This is Pasquale's remark, no? Also? E3 and E4, they really look alike.
Yeah.
What's the difference?
They're just reversed, right? So E3 is, I would guess we would call it suffix free.
Yeah.
The endings of words are unique.
For all those culture who read from right to left, they would much prefer E3 than E4. Yes, let me just make a quick remark. Prefix codes, because of that reason, that you can decode them instantaneously, prefix code are also called instantaneous codes.
You still need like a memory though, because the code words are not length 1. So you read the first symbol and then you need to store them in your memory until you get to the end of the longest code word or whatever, like until you know it.
Yeah. You never need to overshoot, but you need to think or to look at the list often, but you can just go and read from left to right. And so what does, concretely speaking, instantaneous code means is that you can decode the symbol without having to read the head. You read the last bit of the code word and you know how to decode it. Unlike in the other case, we had to go ahead and then backtrack. Any questions?
What was the definition of uniquely decodable again? Prefix code is stronger?
It was that the extension of the code is non-singular.
Oh, right.
So now if you're understanding it as a code over A star, from A star to B, that is non-singular.
Yeah, basically if you concatenate, there's a unique way of reading it. You can't have multiple decodings
Of the stream.
And does prefix code imply uniquely decodable?
Yes. Some people might like figures. I think, Will, you're the
I do like
our god of figures. Yeah. I'll make a figure for you. We have all codes. And as a subclass of codes, you have non-singular codes. As I said, for some authors, this is codes, only non-singular codes qualify as codes. And as a subclass of them, you have uniquely decodable codes. And as a subclass of them, you have prefix code. Like E4 was here, E3 was here, E2, and E1 is here.
So in the one example of a uniquely decodable code, we saw that it wasn't a prefix code, but it did have this property that it was like a reverse prefix code. Are they all like that, or do they all have some, I don't know, some way of reading them that they're like prefix codes but read in a different order or something? Or no?
I don't want just to tell you my guess. I'm really thinking hard about it.
Maybe it's a homework question.
It would
Come
be
up
another
with
good
one
homework
that's-
question. Thank you for proposing homework questions. I love it.
So I have
There are criteria to qualify uniquely decodable codes, like what is the minimal set of criterion for them. However, the reason why I'm going all the way to prefix is that at some point we just prefer prefix codes.
Yeah.
So we're going to develop criteria for prefix codes. And I don't know much about what are the necessarily insufficient criteria for being uniquely decodable. I'm sure there are results about it, and I can look it up, or I can make an homework question if we're all interested into it.
But if a code is both a prefix and a suffix code, just as a question for a discussion, but can it may be the case that this implies that all the codes for each of the letters of the source alphabet must be of the same length?
No. They're not of the same lengths.
Yeah, but in that case,
He means prefix and suffix.
and suffix at the same time.
If I take a prefix code and I construct a suffix code by flipping it,
No, he means a code that's both a prefix and suffix. The
At the
words are
same
like
time.
palindromes or something.
oh,
No, they don't have to be palindrome. But
aren't they then fixed length?
yeah,
That's his question,
Oh.
yeah.
which
Yeah.
would make sense because in practice we use a lot of codes that have like fixed lengths
Yeah,
for each symbol.
ASCII. No?
Yeah, like I send you an 8-bit
ASCII, yes.
letter.
8-bit.
Like I send you 8 bits, and that's a letter, and all my letters are 8 bits.
Yeah, constant size code words is a trick. You're guaranteed to have a prefix code if you have constant size. So you know, in particular, it's going to be uniquely decodable.
It's faster for the code. If it's fixed size, it's faster to go because you just like take 8 bits, you look it up in a table and that's it.
Exactly. Yeah.
If it's smaller, also ASCII, you don't on a computer you don't access a bit. You have to do some bitwise operation to get a bit out of a byte. So it's much more expensive computation. Why you want much more details?
But you mentioned UTF-8,
UTF-8 is pretty much the same thing.
but it's not fixed length.
No, but the first 2 bits tell you how many bytes follow.
Yeah. Oh, okay. So then there's a finite.
Yeah.
Because suppose I want to build, as I told you,
Yeah, there's
my knowledge of concretely how computers work, I don't really know. But if I'm to build an app for texting, the speed at which the numbers of emojis is growing, I need to keep space in my coding alphabet. So I cannot say I'm going to use 8 bits and that's it, because I have only 2 to the 8 symbols to encode. But typically the trick is, we're going to see, we can view a tree to define a code, but you're going to make sure that your tree still has some live branches. So for example, I can use 8 bits for the very convenient letters like A, B, the letters that come up often. But when you have like some fancy emojis, you can encode them further into your bit strings.
Actually, I think they are encoded into words. So you can see it like parentheses, word, parentheses. So you can find a word that identifies an emoji. Probably.
It's depending, because there are many type of emoji. Because there are some that are early inside Ashi, the basic one, like happy faces inside Ashi. There are some other ones that are included in Unicode, but the situation is weird because at the beginning the Unicode consortium have not approved emoji. So some other software, like I don't know, Facebook application was doing by itself, converting some symbol. Okay, I decided this and this is a disaster. So after that, the Unicode consortium say, okay, we can try to include, but the situation is quite unstable today, so there is no a clear way to do it. Because some of they are the conjunction of this sphere character, like she was said, but another type they are really encoded inside the Unicode. And in any case, in Unicode, you have a sort of a blank space that is called user private area, where this space is thought to be always blank, so the user can define his own characters. There are some proposals, I don't know, Lord of the Rings, like Elfic character, you can put it there. So
interesting. Yeah. Okay. Interesting. Thank you. Where was I? Okay, maybe just don't want to hold. Yeah, we still have a bit of time. Prefix sets that are a subset of 0, 1 star can be represented by trees. For example, the image of E4 was the set, this one here, 0, 1, 0, 1, 1, 0, and 1, 1, 1. And a tree, I could start here with my the base of my tree and decide that this side is 0 and this side is 1. And then I had a code word here. So this defines a leaf, and my code word is 0. I follow the arrow. Then if I choose 1, I have 0 again here, and I have 1 again here. This branch dies out, and it defines 1, 0 as another code word. But this branch is still, quote unquote, alive. And it branches out as 1 and 0, and then it defines my last 2 code words, 1, 1, 0, and 1, 1, 1. It's a way to think of prefix-free set of strings. And you right away realize from this construction that indeed no code word is going to be the prefix of another code word. And I will finish with an observation. Observe that. The length of the code words of E4 are now the lengths of the code words. So this is a code word and its length is 1. This is a code word and its length is 2. And this is a code word and its length is 3. And the last one has length 3 also. So the length are 1, 2, 3, 3. And 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 3. That's 1/2 plus 1/4 plus 1/8 plus 1/8. It's 1. In particular, it's smaller or equal to 1. And we're going to finish with basically your question, Will. You asked me how can we characterize uniquely decodable codes. As I said, we're going to be much more interested into characterizing prefix codes, so we're going to have a characterizations of prefix codes. If you come up with a sum of 2 to the minus some length of some code words, and that sum is smaller or equal than 1, then these lengths can correspond to the lengths of code words of a prefix code. Don't worry, I'm going to be writing it down.
Yeah, basically because you can construct a tree from that.
Yeah.
And then just read off the code from the tree.
And so theorem due to Kraft.
Wait, but it's less than 1 or 1?
Less than 1. Yeah, because if I would remove this guy, it's still a prefix code.
Okay. Okay, yeah, I just don't use all the leaves or something.
Theorem due to Kraft. Let L1, L2, ... It could be infinite. Be a finite or infinite sequence of natural numbers These numbers are the lengths of code words of a prefix code if and only if the sum over all n, either finite or infinite, of 2 to the minus ln smaller or equals to 1. And this is known as, this inequality here is known as the Kraft inequality. Are there any questions?
I have one question. The fact that we got 1 in this case, it means that this prefix code can be embedded in a bigger prefix code, right?
Cannot.
Yeah, because
Cannot be embedded. Is that what you said? Oh yeah, exactly. Nicely seen. Yeah, because I would need to add one more code word. This code word would have a length, and this 2 to the minus the length term would blow up my inequality. Yeah. Once we get into Shannon theory, we will see that when they're equal to 1, they fulfill some optimality criterion. For now, I don't need Shannon theory because where's probabilities? We don't need probabilities so far. It's just mapping symbols into strings. So I try to do as much as I can without probabilities. And then to view Shannon entropy, we will need a measure of probability on the symbols that sort of, they come up from a random source with some probability distribution. And then we're going to try to encode them with, as you might imagine, very likely symbols will have short code words. It's more efficient. And very unlikely symbols, like the emoji that does that, nobody uses it, it's going to go into long code words. And that's more efficient. That's going to be the... I'm moving ahead, but for now, we don't need them. Any other questions?
How many prefix codes are there? This craft inequality should tell us, right?
Go ahead and compute it. How many prefix codes are there? Infinitely many.
Yeah, but how much? Either countable or uncountable.
It's going to be countable.
I think it's countable, but I'm not sure.
How many binary trees?
After the courses, I need to write down questions. It's really good. I like it.
Yeah.
And by the way, I did that as a joke, but you understood the vibe of the course. I love it. If you can have questions, and I think they're really good questions, I'm really going to make them into homework. Homework. Problem sheets. It's more meaningful when it's our own interests that we go and investigate. And I think that should be the purpose of especially at the graduate level. I want you to investigate your own curiosities and not just, follow magistral courses.
Why does it matter if we can count them or not?
If it's countable or not?
It doesn't, I don't think, but I was just curious.
Yeah. One characterization of a prefix code is its set of code words. Now, a priori, the number of subsets of a countable set is uncountable. So maybe your answer is uncountably many, but I would need to find an argument from
The power set of the naturals is uncountable, right?
Yeah.
Yeah. Okay.
Mm-hmm. How many subsets of a countable set there are? You can see it by saying either my element is in my subset or is not in my subset, and that defines a bit for each member. So that's a real number, because each real number has an expansion into an infinite string of bits.
This means that a lot of these are uncomputable.
Well, Will's question is, if we restrict them to the prefix sets, then does this reduce to a countable set?
And the answer is no, right? I mean, you said that the answer is no.
I don't know.
Oh, okay.
Because I thought Will was debating, is it finite or infinite? So I re-jumped the question to him with, I was convinced that the answer was infinite, but then Will was debating, is it countable or uncountable? Quickly like this, I don't have an answer.
Yeah, so Giacomo said something very quickly which could lead to the answer. Just count the number of binary trees.
Yeah, it boils down to that.
But that I also don't know if that's countable or uncountable.
The course is over. We can stay if you want. We have fun conversations.